All right, so now we can carry on with chapter 11, which is what we started last time. And so let's go back and revisit what we were doing. So, first of all, chapter 11 is all about inferences about population variances, both confidence intervals and hypothesis testing. And of course, as you saw last time, in order to do this, we do need to introduce actually two new probability distributions, one of which we've seen so far, which is, of course, the chi-square distribution. So what I'd like to do is go back and revisit the chi-square distribution to remind us what its properties are, and then we'll go back and look at what we're using it for. So anyway, there is one nice diagram in here about the chi-square, so you can see it more easily. But in a nutshell, here's what we need to know. Okay. So first of all, a quick reminder. This is the Greek letter chi, even though it's spelled chi, it's pronounced as if it were spelled ki, I guess, or kai. Actually, either one of these could be mispronounced. I guess this is probably the one that is the most realistic. Um, it's called chi. The distribution is chi-square. Okay. And we'll always write it like this. Okay. So, what is this chi-square distribution? Well, it turns out that it is a function of the standard normal distribution. And in fact, that's not unusual in statistics. A lot of the very advanced distributions that you'll see maybe later on in the course, or maybe in a more advanced course if you get that far, maybe you'll decide that stats is your thing and you'll want to take more courses in graduate school, let's say. But whatever happens, many of the advanced distributions are derived directly from the more basic ones, like the normal and the t. So this distribution is derived from the standard normal distribution. Okay. And specifically, what's happening here is that um, a chi-square random variable is the sum of um, standard normal random variables. Sorry, the sum of squared, that's the key detail. Okay, so in other words, if you can imagine the setup looks like this. Here's chi-square, and the subscript represents degrees of freedom. And what happens is we simply add up the squares of n, whatever n is, squared standard normal random variables. Okay. And that's where it comes from. Now, what are the consequences of this definition? All right. Well, let's see. All right. Well, for one thing, of course, it has to be continuous because it's constructed from a continuous distribution. Number two, it is only defined for positive values. Um, no negatives, in other words. Three, it is positively skewed, not symmetrical, like the standard normal is. And I guess that's all we really need to say for now. So let me show you what it looks like. Oh, I guess maybe I'll add one more. The shape depends on the degrees of freedom. I guess, but that's true for any distribution that's characterized by degrees of freedom. But still, as you saw here, the shape does depend on the degrees of freedom. As we keep increasing the number of degrees of freedom, the curve keeps shifting to the right, and it looks a little bit more like the normal distribution, except that it does not have any negative values. Okay, so it looks like this. So you can see that it's positively skewed and starts at 0, cannot have any negatives. And also, I just want to point out too that the values that you'll see under this curve are quite large compared to what we're used to seeing because it's a sum of squares. Okay, so with the standard normal, if you remember, the values rarely go outside the range from negative to +3. Here, the numbers are first restricted to being positive, but then they can be extremely large. They can go over 100, as a matter of fact. So it's something we just have to get used to. Okay. Um, right. So anyway, with all that being said, what we're going to do is two things: confidence intervals and hypothesis testing. So here they're deriving the confidence interval for the variance of a population. All right, now here's something we do have to get used to. If you notice, with the standard normal, the critical values would look like this. We lose that here because the distribution is not symmetrical. So we have to be very careful with the way we write these critical values. And also, the thing we have to watch out for too is that these areas, these are right tail areas, something else we're not used to seeing. Okay, so for example, whatever alpha happens to be, um, alpha over 2 would be here. And then this one, chi-square 1 minus alpha over 2 belongs here because the shaded region is alpha over 2, but that implies that this area is 1 minus alpha over 2. So again, here everything is done in terms of the right tail instead of the left tail. So we have to get used to that. Okay. So anyway, here's the formula for constructing confidence intervals about the population variance. And you can see that the denominators are taken from here. And you can see chi-square alpha over 2 is the larger of the two. So that goes here so that this becomes the smaller number. And then, of course, this is the smaller of the two, and that goes here so that this ratio is the larger of the two. If we want to do the same thing with standard deviations, it's just a simple matter of taking square roots. All right. So those are our two basic confidence intervals. Okay, now, um, I think they have an example waiting for us. Yes, here it is. So we did this the last time. Let's look at it one more time. We have liquid detergent bottles being filled. Let's say this is Procter and Gamble, and we want to make sure that the bottles are being filled correctly. So the premise of this question is that if the variance or standard deviation of the amount of liquid in each bottle is too high, then the amount in each bottle is inconsistent. In other words, you're going to have bottles that are too full, they're not full enough. We don't want that. We want them all to be the same if possible. In the real world, it's not possible for them to be literally identical to each other, but we want to get as close as possible. So therefore, there's probably some target variance or standard deviation that they're aiming for. Anything above that would be unacceptable. Okay. So, you see a lot of quality control problems done this way. We're trying to find out if the variance is too high, which would indicate that there's something wrong with the production process. So what they want us to do is take a sample. Well, they want each one to have 16 ounces. So we take a sample of 20 containers, and they would like to find out. Here we go. Now, in order to do this confidence interval, we need to know the sample variance. So that's all we need, except we need to know what confidence level to use. And let's say it's 0.05. Now, for this case, the degrees of freedom is n minus one. Okay, so keep that in mind. With this kind of interval estimation, the degrees of freedom is always n minus one. So what do we know? All right, well, first of all, in order to construct the confidence interval, we need two critical values. All right. And now we can look them up in the chi-square table. I showed this to you last time. Let's take another look at it. And again, remember, always look in the right tails for the area. I know we're used to left tails from the normal and the t distributions, but here it's got to be the right tail. And it says it right here in the top, so you don't forget. So we need the tail area that comes from the top of the chart here. Let's see. I think it's possible to write on here. Yeah. I noticed about PDF, they really go out of their way to make things difficult. You'd think there'd be a little pen tool or something up here, but that would be too easy. Maybe it's this thing. All right, I'll have to work with that. It's a highlighter, but I'll use it. All right, so we've got a tail area of 0.025 here, combined with 19 degrees of freedom down here, where they intersect. That's what we need, 32.852. And then we now need for the other critical value, 0.975 here. Still with 19 degrees of freedom, 8.907. And those are going to get plugged into this formula with the rest of the information. All right, let's do this. So remember, the sample variance was given to us here as 0.0025. And this critical value, chi-square alpha over 2, is 32.875. All right, now for this one, the numerator is the same. The denominator is the 8.907. All right, so now you just take out your calculator and let's see what we get. All right, the first one is approximately 0.00144, and the second one is approximately 0.0053, 533, let's say. So for the standard deviations, we simply take the square roots and let's see what that is. Um, 0.0379 and 0.0730. Okay, so now they may have rounded it slightly differently. Yeah, they did, but it's the same. And this is our 95% confidence interval for the standard deviation. We don't really the one for the variance is important, but it's very difficult to interpret it correctly because variances are measured in squared units. Normally, it's the standard deviation that we're interested in. Okay, so this is the one we want. Now, they have to decide if this is acceptable or not. I mean, they didn't tell us what would be considered unacceptable, but this at least they know they have a good sense of what the standard deviation is. And if that's too high for them, they'll have to make some changes to the production process. If it's fine, well, that's great. Okay, everyone's happy. Okay, so now we're going to do a hypothesis test, the same situation. Here's how we write hypothesis tests for the variance. And it's just exactly like the previous chapter, except it's the variance instead of the mean. First, we have a left-tailed test. Then we have the right tail test. And of course, we have the two-tailed test. All right. So those are the three possibilities. And the test statistic is here. All right. And of course, this is the hypothesized variance. S squared is the sample variance. And of course, n is the sample size. Now, here, we're kind of restricted to using the critical value test statistic approach because the calculator doesn't actually have the functionality we need to do the p-values. It's kind of disappointing, but there it is. So, of course, the critical values depend on whether we have a left, right, or two-tailed test. So for the right-tailed test, all right, so we have chi-square alpha. The right tail is alpha. For left-tailed test, so this one is referred to as chi-square alpha, sorry, 1 minus alpha, because this is alpha, which means the right tail is 1 minus alpha. And then the two-tailed test is what we were using for the confidence interval. All right, we have two of them. And that's because this area is alpha over 2, as is this area. And the area to the right of this one is 1 minus alpha over 2. It's all right tails with a chi-square distribution. And then you compare them the way you normally do, and you draw your conclusion. Okay, so why don't we try one? St. Louis Bus Company. All right, so the St. Louis Bus Company wants to promote an image of reliability by encouraging its drivers to maintain consistent schedules. The company specifies an arrival time variance of 4 or less when the arrival times are measured in minutes. So we're going to find out if the actual variance is too high to be consistent with that rule. So this is a right tail test because we're looking for evidence that the variance is too high because that would mean something needs to be done. All right, so it's a right tail test. Alpha will be zero point zero 0.05. Wait, it doesn't say. Hold on. I don't want to jump to conclusions. It's easy to do that. No, it's zero point zero 0.05. Okay. As we just saw, the test statistic is chi-square is n minus 1 s squared over sigma squared. And now they've got to give us some data. We have 24 buses, and the sample, aha. See now, unfortunately, there's a typo here. It says sample variance, but it says S2. I have a feeling that what they meant was this. Yeah, you can see because they put it here. All right, great. What else do we need? Well, we know the hypothesized value of the variance is 4. All right, so let's plug in these numbers. And we'll get 28.175. And the critical value, for this, we need the degrees of freedom. For this application, it's n minus 1. So we need, so I'm going to write it like this. This is not standard notation, but I'd like having it all together in one place. The tail area is zero point zero 0.05, and we have 19. Oh, wait, I'm sorry. We have 23 degrees of freedom. That was the last problem. 23, because it's n minus 1. I'll write that here. Much better. Okay, great. So let's look this up in the table, which I just happen to have right here. So, wow, I'm not sure how to erase these orange marks. All right, it's all right. We'll work around it. So we have 5% in the right tail. Oh, I know. I'll change the color. 5% combined with 23 degrees of freedom is 35.172. Okay, and so this is our rejection region because it's a right-tailed test. But the test statistic was only 28.175. And we know what that means. That means we do not reject the null. And now that means that there's nothing wrong with the bus arrival times. Okay, which is good news for the company. And that makes everyone happy. Okay. So there's not enough evidence to show that it's too high. It appears to be fine. All right. What are they going to have us do now? See, now the p-value is there, but the calculator doesn't have the chi-square built into it that we need. It would have to be the inverse of the chi-square distribution, and it has the chi-square, but not the inverse. And that's what we actually need here. Anyway, so let's not worry about that. What they do is they look in a table to see the approximate value, but we can skip over. You see what I mean? They can come up with a rough idea with just a table, but it's not absolutely necessary. Now, what if we're comparing two different variances? Just like remember in chapter 9, we only had hypothesis testing about one population mean. Then in 10, we moved on to two. Here we're doing something similar. We were going from one population variance to two. What's different here, though, is that when you move into two, you need yet another probability distribution. Okay, so let's look at this one now. It's called the F distribution. That sounds like a strange name, but it's named after the inventor, which is Ronald Fisher. He was one of the real heavyweights in statistics history, okay, like Newton in physics. So a lot of statistics that we know were developed by him. Anyway, so how is this one different? Well, the F distribution comes about like this. So, in other words, it's constructed from the chi-square distribution, okay? Just like chi-square is constructed from the standard normal. But if you notice, um, there's more than just that. It's constructed from the ratio of two chi-square random variables, each divided by its degrees of freedom. So what this means then is that like the chi-square, the F distribution is only defined for positive values. Hold on one second. Let me enter this. It is also skewed to the right and discontinuous. So if I drew a picture of it, you'd be hard pressed to see the difference between the F and the chi-square. Oh, it does look a lot like the chi-square, doesn't it? And there's a reason for that because of the way it's derived. Okay. Now, here's one of the quirky things about it, though. The F distribution is characterized by two different degrees of freedom, and they're called the numerator degrees of freedom and the denominator degrees of freedom. And obviously that comes about because of the way it's defined. In other words, let's copy this down here. And whatever this number is, this is clearly the numerator, degrees of freedom. And this obviously must be the denominator, degrees of freedom. Now, that causes challenges for making tables about the F distribution. What challenges would those be? Well, let me show you what this table looks like. All right. Oh, let me find one. Hold on. Oh, now this is where it gets interesting. You need to look up a value with the F table, two different degrees of freedom. The top row is the numerator, degrees of freedom. This column is the denominator, degrees of freedom. So where does that leave room for alpha? It doesn't. Each table is good for one alpha only, and it's listed here. Okay, the chi-square, there's plenty of, all these are alphas across the top. If you see here, for alpha equals right tail area, we can have all the alphas we want because there's only one type of degrees of freedom over here on the left. But when we need two different degrees of freedom, all of a sudden we need a new table for each possible value of alpha. Wow. So the three of them that you'll see in Brightspace, or Blackboard rather, are the ones you'll see here: 5%, 2.5%, and 10%. That's all we have. That's all we need. Okay. But always remember, numerator degrees of freedom, denominator degrees of freedom. Don't get them backwards because you'll get the wrong answers. Okay. You've got to be in the right order. And yes, you'll see. I think I have Blackboard open here somewhere. Yes, here it is. So if you look in chapter 11, you'll see why way down here at the bottom. There's one table here that only applies to 5%. I also went ahead and created these three in Excel, 0.025, 0.05, and 0.10. So these are the ones we'll be using. We don't really need this one. I should probably hide it. Okay, just to avoid confusion. Okay, but with that all said, the rest of this is very straightforward. Um, oh, okay, there's one difference. There's one peculiar difference, though. Let's see, they're going to start us out with the hypothesis testing, so let's see what's going on there. Now, oh my God. Well, there's a very significant difference here, and that's because of the way the F distribution is constructed. And this, it would look like this, as you can imagine. It's the other part that's different, the alternative hypothesis. There's a strange twist here, okay? And that is there are only two possible alternative hypotheses. So, in other words, there'll be the two-tailed case, which is exactly what you would expect. But then instead of having left and right, we have one-tailed test only. And you see how it's written? It looks like it's a right-tailed test. We don't have a left-tailed test. We have a one-tailed test. Okay. And so both possible cases are lumped together as a single case, the one-tailed test, but it's written like this, and there's a good reason for that. Um, yeah, all right. Well, anyway, I'll tell you what it is. Um, it's to do the F statistic. And just like before, but here's the strange part. So, in other words, all of a sudden, for the first time, it matters which population is one and which is two, because we have to make sure, we must ensure that the numerator variance is greater than the denominator. So, in other words, we have to make sure that we chose them correctly. So, I don't want to see sigma 1 squared being less. That means I've got them backwards. Okay. And so that means that we don't need a left-tailed test. We can't have a left-tailed test by setting it up this way. Sigma 1 squared is, by definition, always greater than sigma 2 squared. So this is what we mean by a one-tailed test. The two-tailed test is fine, but this one, there's just the one case. Now that's very strange compared to what we're used to seeing. But again, it's because of the way the F statistic is just defined. So this is something we have to get used to. One more thing I want to mention here that with this test statistic, so in other words, when it comes time to looking at your table, you need to have 2 degrees of freedom. As we saw before, the numerator equals n1 minus 1, the denominator equals n2 minus 1. Okay? So now, with all that being said, we can do the first example. All right, so here's the two-tailed test. And oh, and by the way, we since we don't have access to the population variances, we're going to write as when we actually calculate the F statistic, it'll look like this. But again, we have to make sure that the numerator is larger than the denominator. Otherwise, we have to reverse the two. Um, the one that we call population one has to have the larger variance, and population two has to have the smaller variance. All right, so that shouldn't be too tricky. All right, anyway, where's that first example? Here we go. Dulles School County. They want to select between the Millbank Company and the Gulf Park Company for the bus service. It's the variance between the two that will be used to decide which one to pick. Clearly, we want the one that's smaller. Okay. So we're going to start. Oh, all right. So they want us to do this as a two-tailed test. The way they wrote it, it didn't sound like that. But all right, let's do this. Alpha is 0.10. I just realized I never wrote down the critical values, did I? All right, let's take care of that right now. The critical value is the F statistic. Well, I guess we don't have to write it down separately. It's the value you find in that table. Um, so that's all we really need to know. We don't need to write it separately. We're going to look it up in the table. So I guess we don't need a separate formula for that. So instead, let's do this. Okay, hold on one second. See, here they're just explaining it in terms of the p-value. I guess we could write it like this. No, we'll just leave it like this. So here's the data. Millbank and Gulf Park. All right, here we go. So Millbank has 26 in its sample. Sample variance is 48. And for Gulf Park, it's 16. And the variance is 20. Okay. All right, so we can think of Millbank as population one and Gulf Bank as population two because the variance of Millbank is greater than from Gulf Park. So we can leave it like this. So the test statistic is 48 over 20, which is 2.4. Now the critical value is written as, now this is my notation, by the way, just so we can see everything all at once. Not every book does it this way. So I just want to mention that right here. I think I skipped over that before. The critical values are if this is a one-tailed test, then we just change the alpha to, I mean, we leave the alpha the way it is. If it's a two-tailed test, we cut it in half. But the degree, the numerators and denominator degrees of freedom only depend on the sample sizes. So the alpha itself depends on whether it's a two-tailed test or a one-tailed test. So here's a two-tailed test. All right, so we need, so remember from up here, alpha is zero point zero 0.05, zero point 0.10. The two degrees of, sorry, the two sample sizes were 26 and 16. All right, so we end up with 15, no, sorry, 25 and 15 degrees of freedom with 5% in the tail area. Now we get to look it up in that special table. And so here's where we have to be super careful. First, pick out the right table. 0.05 is the right table here. So this is clearly not the right one. Here it is. So make sure it's 0.05. Now, the degrees of freedom in the numerator is 25. Oh, bad luck. We don't go that far. So I don't know where they got this information from. Let's see. That was very unfortunate. Oh, they gave us their own table. That's why. See, they've set it up a little bit differently, though. Keep an eye on that. They've got tail areas over here, and then a handful of degrees of freedom. So if you notice what they've done, they've got numerator 25, denominator 15, alpha is 0.05, and that's going to give us 228. I guess, I mean, you could have a table like this with all the different degrees of freedom, but then it gets big in a hurry. If you don't want to do that, you can do it like this, 2.28. All right, wonderful. That's our critical value. And this, of course, is the rejection region. But the test statistic was 2.4. Uh-huh. So you can see we just barely made it into the rejection region. So if remember, this is a two-tailed test. So because we're in the rejection region, or the test statistic is in the rejection region, We will. All right. So we reject the null. Whoops. So in other words, we have evidence that the variances are different. So what that means is that between the two choices that they have, between the two companies, they do not have the same variance, which means obviously we're going to pick the one with the lower variance, or at least that's going to be one of our considerations. So therefore, they do have different variances, and we can do whatever we want with that information. Okay. All right. Now I see that they did not. Maybe they will later on give us a confidence interval for the difference in the variances. I guess that means you don't have to do it. So we have in this chapter, besides introducing the chi-square and the F distributions, we know how to test hypotheses about a single variances. We're going to construct confidence intervals for a single variance, and we can test hypotheses about two variances. But they did not give us any confidence interval formulas. That means that we're not responsible for that. Now, they did also give us some Excel examples that we want to look at. Now, one of these does require the data analysis tool pack, which I remember last time some people don't have it. So if you're one of those people, then you don't have to worry about this part. But let's see what we can do. So the first one, if you remember, this is the confidence interval for the liquid detergents. And we did it already with a calculator, but let's try it with Excel. All right, here we go. So the spreadsheet for this one is called detergent with annotations. The annotations means that I had to do all the typing. Okay. So here's the data. All right, let's try these. Sample size, count, and that's A2 through A21. Now the variance, you have to watch it because they mean the sample variance. And the command for that is var.s, again, A2 through A21. And of course, they told us that, but we want to do it with Excel. Confidence coefficient, this one was 95%. Level of significance is 1 minus that, which means that's our alpha. Ah, now the chi-square. Now we need to know how to do this in Excel. Here's the command. Chi-square dist, I think. No, it's INV. And the parameters it wants, oops. See, Excel has, this is the function we would need to do p-values. And Excel has it, but the calculator doesn't. Chi-square INV, D7 over 2. So in others, that's alpha over 2. And, oh, degrees of freedom, sample size minus 1. You recognize that number. And then for the other one, we have probability. This time is this is the right tail, which means alpha over 2. Still degrees of freedom. D3 minus 1, 19. Oh, wait. Whoops. Oh, I forgot the one minus. There you go. In other words, it's one minus the alpha over 2. The point estimate is our sample variance, D4. And then the lower limit is, so it's degrees of freedom, or n minus 1, times s squared, all divided by, in this case, you're dividing by the the larger of the two, and there's your 00145. The upper limit, again, is n minus 1, sample size minus 1, times s squared, all divided by the smaller of the two critical values, and that's the upper limit for the variance. Okay, so that one's finished. Now, by the way, if you're watching this at home, you can go ahead and feel free to send it over to me because I am going to collect these, but because we're not meeting in person, we'll run through this again on Monday night. And if you're not doing this now, you can take care of it on Monday night. Okay, under the circumstances, if you're doing it, over the weekend, that's wonderful, but you can do it on Monday as well. Okay, because I know you're not there. I mean, really. So then we have, how about the next one is the St. Louis Bus Company, where we have a hypothesis test about whether the bus's variance is more than 4. So that spreadsheet is called school bus. Oh, no, sorry, that's the wrong one. Bus times, that's it. So just like before, some of this we have to do it ourselves. The sample size, the sample mean. So here the data is found in cells A2 through A25. Okay. And then the sample mean, same thing. That would be A2 through A25, and then the sample variance VAR.S, A2 through A25. The hypothesized value is 4. The test statistic is this one. We've seen this before. N minus 1 times S squared, all divided by the hypothesized value of 4. Okay. Degrees of freedom is N minus 1. Sample size minus 1. Oh, but what about these? Good question. P-values. Now, again, remember, this is something we can do in Excel, but not on the calculator. So what commands will they give us? Here we are, chi-square dot dist, as opposed to inverse, which we did in the last spreadsheet. Um, it's not enough. It's got to be dot RT for right tail. And then we'll have D9, which is the test statistic. And then you need D10. Oh, that's still not enough. Oh, I see. True. Hmm. The second one doesn't say true. I wonder why. You could put true or 1. We'll just try this. Oh, and I just noticed I forgot the equal sign. So that's a typo. This true doesn't belong here. I was surprised to see it there. That's for a different command. So we'll get rid of the true. And for the upper, X again. This time the X is D9. Oh, no, it's D9 indeed. Oh, now I understand what happened. This one is not right tail, but this one is. Oh, but right tail. Okay, that's that. Now I know what's going on. The chi-square setup is very strange in Excel. Let's go through that one more time. It's chi-square dot dist RT. Sorry, not RT. I keep getting that backwards. But then if you don't have the RT, you need to tell it that this is true. But for this one, we're using chi-square dot dist. This one is RT, the right tail, which means we don't need to tell it true. I don't know why they set it up that way. It is a little confusing. And then two tails, it's that same setup they always have, equals two times min of the two. So it's a very high p-value, which means we do not reject the null. And that's what we discovered when we did this in the slides or the notes. And that, remember, the St. Louis Bus Company, they do not have to make a change in the scheduling because we were not able to reject, we were able to, sorry, we're not able to reject the null. All right, here it is right here. This is the St. Louis Bus Company. So we did not reject the null. There was nothing wrong with their scheduling. Okay. And you can see this confirms it because now we have p-values to look at right there. That's way too high to reject the null. All right. So again, why don't you hang on to this, save it or send it to me, or we'll do this on Monday. And then the last one is the Dulles County school buses. Here we're comparing Millbank with um, Gulf Park Company. So this time we're using the F distribution. By the way, this one is called school bus. So you get the data over here. Now this one is being used with the analysis tool pack. We don't have the well, all right. Well, maybe we could have done it without the tool pack, but this is what they are asking us to do. So the one that we need is called F test to sample for variances. Okay. So we come over here, data, analysis tools. Oh, mine is not installed. There it is. Okay. There's only one F test in here anyway, so that's easy. Variable one is Millbank. Make sure you include the header. Variable two is Gulf Park. And then click on the labels. Now remember, this one, alpha was 0.10. And I'm going to have them put the output on the same sheet, F1. There it is. It's very simple. It doesn't tell us what the critical value is, but it does give us the test statistic. That's the 2.4 that we found. Okay. Where is it? There it is. And then we have a p-value. See, oh, I see. That's only for one tail. We had two, so we'll stick with this part. All right. So again, if you're watching this, you can save this and send it back. Otherwise, we'll go through it one more time on Monday. And then Believe it or not, we're done with chapter 11 already. It's a fairly complicated chapter, but at the same time, they're really just basically introducing us to the two distributions. In chapter 12, we're going to get to see some very interesting applications of the chi-square distribution. Okay, so that we have that to look forward to. So let me just, yeah, that's it. That's all they have. All right, good. So when we meet up on Monday, we'll go through these spreadsheets one more time, and then we'll start chapter 12, which is all chi-square, okay? And so I'll see you then at our normal time. All right. In the meantime, good night.